Hello, everybody. This is a video on the twin paradox, in case you missed class or need an overview of how it works. So the whole idea is that from two different reference frames, and by the way, this is just going to be kind of a brief overview. For the assignment, please go through the details on your own. But this explains a lot of the setup, which obviously is one of the most important parts. So from the Earth reference frame, because that's the whole point, what the Earth sees, so here's the Earth, is that a rocket, right, goes at 60% the speed of light toward Barnard's star, which is from Earth's reference frame 6 light years away. So, and then it turns around and comes back. So then it goes at negative 0.6 c because it's to the left. We'll call that negative. So if I were to graph distance versus time in the Earth's reference frame, and remember, Earth's time we call t prime. So this is always a graph of x versus t prime. What we get is that at 6 years, right, the rocket, when at v equals 0.6 c, which by the way, you automatically want to solve for gamma, which you get 1.25 for that, which you guys already did. And then it stops there. Now it's worth it to plot Earth's world line and Barnard's star world line. I'll draw Barnard's star in green, right? The star is in green. It's not moving in this reference frame, and the Earth is not moving in this reference frame, right? So Earth and the star are just going through time. They're moving through time, but they're not moving through space. So they actually are moving. So their world lines are this and this, respectively. And the rocket goes through space-time and goes from Earth to the star. And then it turns around and comes back to Earth. And on Earth, that was 20 years. How do we get 20 years? Well, L equals V times T prime. So 6 equals 0.6 times T prime. So T prime is 10 there and 10 back. Right, 10 there, 10 back. Great. Now, what is T? T equals T prime. So this was on Earth. T equals T prime over gamma, which is 10 over 1.25, which is 8. So everything I just did is hugely important. This is like the whole point, which is that in this reference frame, 10 years elapsed. And in the rocket's reference frame, 8 years elapsed, because we time dilate that the time elapsed on Earth. So this is only 8 years, which I'll write like this, and we can even draw a new like axis of time stamps, right? Notches, like a graph. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 20. And here we have 1, 2, 3, 4, 5, 6, 7, 8. Time is elapsing along this line differently, right? So it's elapsing only 8 years here and then 8 years here, right? And so it's a total of 16 years for the rocket. So if you draw the light lines from Earth every 2 years, draw them at a slope of 1, right? Remember, this is a slope of 5/3 because the slope is always 1 over the velocity in a space-time diagram. And so the velocity at the speed of light is a slope of 1, and you just do a system of equations to figure out where it hits the rocket, right? Where do each of these hit the rocket? And you're going to get a very interesting result, especially coming back. And see if you can have every 2 years. If you mark it well and you follow the instructions, you'll notice that every 2 years, right? If you do v equals negative c, excuse me, from the rocket, if you draw it accurately on your graph, light will have a slope of v equals c is slope of 1. V equals negative c from the rocket, because it's going to the left, will be a slope of negative 1. And just draw the line, and you're just going to intersect lines. That's all you're doing, right? And if you want, you can just draw it accurately, and it'll meet at integer locations. What you can also do is go through it and figure out where this point is, because that's 2 years in the spaceship. Where is that on Earth? Where is that on your coordinate reference frame? You guys can figure that out because you know the dilation. Work through it. You can do it, right? Figure out when it hits the Earth and when it hits the rocket. If it was emitted every 2 years from the Earth, boom, 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 when did it hit the rocket? And if the rocket emits it every 2 of its years, 2, 4, 6, 8, when does it hit the Earth? That's it. If you need to rewind and go through it, that's just what you're doing. That's part 1. Boom. Part 2 is, so if you need to rewind that last part, rewind and go through that slowly. Just slowly. All you're doing is looking where lines intersect, and you're using the equations in tandem with the graph. Try it and just spend some time with it. It might not be quick, but if you methodically go through it, you're going to get there. It's a great practice of using those skills. Part 2 is the rocket's initial frame. Initial is the whole point. And you guys remember from class, that's the whole solution to this paradox, is that the reference frame changes for the rocket. So v equals 0.6 c to the right, we're going to have an eyeball in space. This is my eyeball. Follow the rocket. And the eyeball is going to keep going, which means according to our magic eyeball in space, right, velocity is 0, which means the velocity on the way there for the rocket is 0. And it sees the star coming at it at negative 0.6 c. And it sees Earth go away from it at v equals negative 0.6 c. On the way back, the rocket turns around, right, and goes at v equals negative 0.88235, I think it was. You want all those decimals. I know on the red sheet I wrote 0.882. But if we have all those decimals, it works out nicely. That is a gamma of 2.125, I think. Something, something, something. So you want that to be accurate as well. So that means the Earth has a gamma of 1.25, and so does the star. But the rocket is just a gamma of 1. So if we graph this reference frame, first of all the values of x are negative. The star starts out, if we start out here, the Earth starts out, we'll do the Earth in blue again, here, and the Earth goes away at negative 0.6 c. I'll do the rocket in red. The rocket, actually, maybe I'll do the rocket in black. The rocket's world line, v equals 0, follows the reference frame. It's not moving for how long? Well, now t prime equals 8 years. If you remember, that was the whole worksheet we did in class. That from this reference frame, the rocket sees the Earth move. That's the paradox. So it's only 6.4 years on the rocket. 6.4 years on the Earth when it's 8 years on the rocket. Because the rocket sees the Earth as time dilated. So who's right? Which twin is younger? Well, the whole point is that this will never be resolved until they meet in the same place in time again. So the answer is who turns around makes a huge difference. So the rocket at that point, once it reaches the star, technically it doesn't reach the star. If I walk into a wall, it's the same as if the wall walked into me. Think about that for a second. You see how it's the same thing. I mean, your face would feel the same, but it literally is the same thing. It's relative. Me moving into something is the same as it moving into me. So when it reaches the star, it's actually the star moving into it. The star had a positive value. I'll do the star in green again. And the star was moving at a parallel speed, right, to the Earth. So this is the Earth. In blue, Earth. In green is the star. And when the star hit the rocket, it took 6.4 years for the star as well, according to the rocket's reference frame. The rocket turns around and speeds up and catches the Earth, because the Earth is still moving at negative 0.6 c. It never changed reference frames, but the rocket did. So the question is, when do these intersect? And if you use the time that elapsed between when the rocket turned around and when it crashed into Earth again, or softly met Earth again in space and time, you can figure out the time dilation for the rocket. And you can figure out the total time elapsed for this eyeball in space that continually moves. The star is still moving past the eyeball. The eyeball is just chilling there in space, watching this whole event go down. The Earth and the star are moving past it. The rocket was moving with it, but when the star hits the rocket, it turns around and it accelerates toward the Earth. Please pause that and replay what I just said. I just said it all exactly as you need to outline it. So please, you can go back and listen to my words. They were very exact. Sorry, I'm not writing it in words on the screen. Here's the diagram that the star came into the met the rocket, and then the rocket turned around and caught up to the Earth. And this comes from the velocity addition formula, by the way, that when you're going near the speed of light, it doesn't work to, if you assume c is 1, and you're in light units, you can just use this formula. 0.6 plus 0.6 over 1 plus 0.6 plus 0.6 means that the total velocity is 1.2 over 1.36 as a fraction. Plug that into gamma, you should get something like that. You can check my work. I believe these are accurate, but I might be off. Please check my work. Please do it on your own, and please map out the time experienced by the Earth. How much time is experienced by the Earth? Well, that's going to be t prime total, which is from here to here, over gamma for the Earth. T is going to be this t prime, which is a shorter t prime, over its gamma for the rocket. Right? We can call it t prime turnaround, or t prime 2, I guess, for the second journey, right, over the rocket's gamma, which is this, of course. Here's the Earth's gamma. If you can sort all this out, that's the whole point. I'm asking you to sort all this out. That's my quick introduction of the setup of the drawing, the physical circumstance, how to interpret the graph, and the formulas you need to use. Please email me any questions or ask them in class, but this, I think, sets it up nicely. And you should get, of course, that the answer from this reference frame is the same as from this reference frame, which means that we have a consistent answer in space-time, that the time experienced by Earth and the rocket are the same no matter what reference frame you're in, and that the rocket is always younger than the Earth because it turned around. That's it. If you have an answer that's invariant, independent of what reference stream you use, then there's your consistent solution. I hope that made sense. That was my quick introduction to a very cool thought experiment. See you guys later.